speaker is Jason Lee for Carnegie Mellon. I don't see him, but I'm sure he's connected because I saw his name.
Yeah, he's here.
Oh, he's here. Okay, great. So he's going to present a faster minimum K-cut for a simple graph. This paper was a co-winner of the Best Student Paper Award at Fox last year, and it gives a significant improvement on the complexity of a natural combinatorial problem that is min K-cut on simple graphs. So as before, the talk will have a length of 25 minutes, followed by 4 minutes of questions and answers. I will maybe signal to the speaker when 5 minutes are missing from the end of his talk.
Okay, so can you hear me?
Yeah, thanks, Jason. Go ahead.
Can you hear me?
Yeah.
Good. Okay. So this talk will actually be on an improvement on this work. It's both an improvement and a simplification. So I thought it would be nice to cover this result instead. This appeared in Stock 2020, so it's a bit more recent than the what will normally appear in Haug 2020. So this talk will actually be on the Karger-Stein algorithms optimal for K-cut, joint work with Anupam Gupta and Yu-Weng Lee. And again, this appeared in Stock 2020. Okay, so let's begin with the K-cut problem. So given a graph, we want to delete the min-weight set of edges to cut the graph into at least K components. So for this talk, think of K as a large constant, say like 100, because that's what regime we'll be considering. Throughout this talk, we'll be considering two canonical graph classes to like build some more intuition on how K-cut algorithms perform on certain graphs. So one is the cycle, and here the opt is just K. So imagine every edge weight is 1. So opt is K, and the number of min K cuts, a problem we'll also be considering, is n choose K, because we can delete any K edges in the cycle to get K pieces. And the other graph we'll be considering is a clique. And here opt is roughly n times K, because the best way to cut this graph into K pieces is by isolating K minus 1 singletons, that causes roughly n times K, ignoring lower order terms. And the number of min K cuts is n choose K minus 1. And throughout this talk, we'll be considering two main questions. One is a more computational, more algorithmic question. How fast can we compute the min K cut? What's the fastest algorithm to compute one? And the other one is a more fundamental fundamental extremal combinatorics problem. Given the graph, how many min K cuts can there be? And here are the prior results for both questions. So before 2019, the best algorithm known was the original Karger-Stein randomized contraction algorithm. And this ran in roughly n to 2K time. And this algorithm also was could output all the min K cuts of the graph. So it could give you a corresponding extremal bound of n to 2K. In 2019, the authors have improved slightly both the algorithm and the extremal bound slightly to n to the 1.99. Okay. And recently, a result by myself has improved the running time down to n to the k for unweighted graphs. This does not give an extremal bound either. So this is just an algorithmic statement. On the lower bound side, the K-cut problem reduces the K-clique problem, reduces from the K-clique problem. So based on popular conjectures on the hardness of max weight K-clique, solving the K-cut is unlikely to be done faster than n to the k time. Finally, on the approximation side, which we won't cover in this talk, to prove two approximations known in polynomial time, it's difficult to do better than 2 minus epsilon. So the major result of this talk would be we have an algorithm to compute the min K-cut in n to the k time. And this algorithm will actually be the original Karger-Stein algorithm. So we'll show that the original simple randomized contraction of Karger and Stein actually outputs a min k-cut in n to the k time. So this is an improved analysis with the same algorithm. And this, again, the Karger-Stein algorithm can also enumerate all the min k-cuts, so you get a corresponding extreme value. So let's begin with the Karger's randomized contraction algorithm for just minimum 2 cuts, not min k-cuts, just to begin with. So the algorithm is very simple. We always. Okay, so we'll get to that later on. What the little one term ends up being. Turns out we can actually remove it entirely, so it'll just be a constant times n to the k, but we'll get to that later on. So the Karger-Stein algorithm is very simple. While the graph has more than two vertices remaining, pick a random edge and contract it. So here, let's assume for the rest of the talk that the graph will be unweighted. So instead of picking an edge proportional to its weight, we just pick a random edge because all the weights are the same. So let's suppose the left graph is our input graph. And if, we always pick a random edge in the graph until we're left with 2 vertices. And once we're left with two vertices, we consider the cut induced by these vertices. So take color one vertex in the final graph red, and take one part of the cut as all the vertices that got contracted that vertex, and color the other one white, and that's our partition. In this case, we got lucky because we actually recovered the min cut of the graph, which is 3. And a well-known analysis of Karger shows that this simple procedure finds the min cut probably at least 1 over n choose 2. This is also tight because a cycle has n choose 2 min cuts. So what is this? So the Karger-Stein algorithm is just a very straightforward generalization for this randomized contraction algorithm for k cuts. So the only change here is we stop when there's 2k vertices remaining, and then once they have 2k vertices, we just pick a random partition of the remaining graph into k pieces. So here let's give us a simple proof, the simple classical proof of why this works. So the theorem we're gonna briefly go over is that this simple algorithm will find the min k cut, some fixed min k cut, but probably at least this quantity here. So the proof will be, let's consider the procedure when there are vertices remain, and let's consider what is the failure condition. The failure condition is we contract an edge in opt. If we ever do that on any iteration, then we destroy the min k cut. So conversely, we succeed if on each iteration we do not contract an edge in opt. So probably a failure is just, since we pick an edge at random, it's just opt over number of edges. And here we're going to use the inequality opt is at most k-1 times the average of the smallest k-1 degrees. Why is that? That's because this quantity here is just a sum of the k-1 smallest degrees, and that induces a min k-cut. That induces a k-cut of the graph because we can just isolate those singletons in a cut, and opt can only be smaller. And finally, the denominators are equal. The number of edges is by a simple handshake lemma equal to the r times the average degrees, which is the sum of the degrees over 2. And now we just use the fact that the average of smallest degrees is at most average of all degrees, so we get this boundary. Finally, what is the probability that opt survives the contractions over all iterations? That's simply the product of 1 minus its failure probability, which we can estimate as n to the minus 2k minus 1. Now, it's instructive to to consider this analysis and see where we've losing this factor 2 here. So we're losing this factor 2. It turns out we lose it from here, and this factor 2 comes from here, which essentially this factor 2 here is because every edge has two endpoints. That's like fundamentally, that's the reason we're losing this factor 2. Of course, unfortunately, this is also tight, so it's not immediately clear how to improve upon this factor. Now, so how do we improve the analysis? Let's first consider the Carter-Stein algorithm on the two. Let's first revisit the analysis on the two graph examples we considered, the cycle and the clique. So for the cycle, the nice thing is opt over number of edges is always k over r when there are arbiters remain. That's because Carter-Stein's algorithm, contraction algorithm, will always contract an edge of the cycle to get another cycle. So the graph will always be a cycle throughout the algorithm. And here, k over r is much better than 2 times k minus 1 over r, which is what we got in our analysis. And this improved factor translates exactly to the running to the final probability of success. So we get a 1 over n to the k probability of success instead of the original 1 over n to 2k. So in other words, Carter-Stein algorithm performs much better on the cycle. So what about the clique? Here, unfortunately, the analysis is tight in the sense that opt is roughly the denominator, the numerator k minus 1 times r, and the number of edges is r choose 2, and we get 2 times k minus 1 over r. So this is tight. Now you might ask, in that case, how do we beat the 2 to the k minus 1 time? So here the key idea is that tight examples like this will not show up over all iterations. So the first step might be tight of the algorithm, but as the algorithm takes more and more steps, with very high probability, this example will no longer show up. So it might be the case that the first iteration is tight, but later on it should not be tight. We should actually be able to squeeze out another factor of 2 once another iterations have passed. And this factor 2 savings exactly corresponds to the final running time of the final probability of success of 1 over n to the k. So now I'll give you like a quick teaser of why such a statement might be true. In particular, for the clique, more quantitative statement we get is that after a while, most of the vertices will actually have degree at least 2n, not n. That's good for us because that increases the number of edges while keeping the opt the same. And the factor 2 we get when compared to the original degree n minus 1 is that exactly what shaves off the factor 2 in this analysis. So let me. So here is why the Carter-Stein algorithm should do better on the clique. If there's one thing to get out of this talk, it should be this one. And the message is very simple. The original Carter-Stein analysis was suboptimal on the clique, and I'll show you why. So given the clique, the algorithm will contract a random edge of the clique. And once the edge is contracted, the new vertex will have degree roughly 2n, not the original degree n minus 1, by a simple counting argument. And now after, let's say n over 2 iterations, a lot of these other edges will be contracted, and they'll all be contracted into vertices of degree roughly 2n, or possibly more if they got further contracted. So in particular, after a while, it's not clear how long, but after a while, most vertices will be contracted vertices in the remaining graph. And these vertices have degree at least 2n, because at least 2 vertices got contracted to them. So once we redo our analysis, we get that, so what is r times the average of all our degrees? Well, initially it was n minus 1, the average of degrees. And after a while, if most vertices have degree at least 2n, then we actually get a factor boost. We actually get a factor 2 boost here. And this factor 2 exactly cancels out the numerator factor 2, and we get n to the k. And we get a probability of n to the k. Of course, this is assuming that this happens soon enough in the contraction algorithm that the the better factors we get dominate the original type factors with the factor 2. So that's essentially the intuition why you should expect the Carter-Stein algorithm to do better than Quique. Okay. Okay. So now we'll proceed to the theorem and the main proof idea. So again, the theorem restatement is that the Carter-Stein algorithm outputs any fixed min k cut with probably at least one over n to the k. So our proof will have two main steps. The first step is a refined analysis of the Carter-Stein randomized contraction algorithm. And the second step is a connection from cuts and graphs to extremal set theory in combinatorics. So here, let's for the rest of the talk define lambda k bar as opt over k. Think of this as the average contribution of each of the k pieces to opt. The second property, what we want is we want a number of we call them small cuts, and they're the cuts of size in the following range to have most linear in n. So here, think of k and epsilon are constants. This factor here is linear in n. And what we want from 1 is that if statement 2 holds, if G has only a linear number of small cuts by this definition of small, then the Carter-Stein algorithm actually behaves much better. Okay, so we'll begin with the first step. So I'll just pull up the slide for a little bit more. So begin with the first step. So for the first step, we'll be considering a more continuous version of Carter-Stein, and we'll see why later on. This continuous view is more intuitive and better for the analysis than the original discrete view, which is just selecting random edge and contracting. So let's imagine instead of selecting random edge on each discrete step, we have a continuous time, and every edge has an exponential clock with rate 1 over lambda k bar. In other words, think of delta as like an arbitrarily small constant going to 0, and it fires independently in each delta time step with probability delta over lambda k bar. And when an edge fires, the first time an edge fires, contract it. So our first, I want to claim that this procedure essentially is a restatement of Carter-Stein in the sense that the edges are contracted in a random order, uniform random order. But the nice thing here now is that because the events in each delta time step are independent, we get the time that every edge contracts is independent of the time of another edge contracts. So essentially, we can decouple the randomness between different edges of the graph and consider each edge on its own. This is in contrast with the Carter-Stein analysis algorithm, where on each step exactly one edge is contracted, so the edges are not independent. So now let's imagine. So why is this view interesting? Let's try to reanalyze. Let's try to reformulate Carter-Stein's original analysis in this continuous setting. So if there are R vertices remaining, again from the previous analysis, we get this many edges at least in the graph. Now every single edge gets contracted with this probability, and now we want to say that a reduction number of edges is roughly also the same as the reduction number of vertices. This is true as long as there are no cycles contracted, because in a cycle, once we contract all the edges except the last one, then the last edge we contract, but we do not reduce the number of vertices. So this is assuming that no cycles are contracted. But when delta goes to 0, this should be true, because this quantity itself is much less than 1. So this means that the factor R decreases by this factor at least, by this factor in expectation in each delta time step. So that means after t time, which is like t over delta time steps, the expected number of vertices remaining is this quantity here. So we should expect to stop at time roughly at most 2 ln n, because that's when this quantity is like roughly 1. And what about fixed min k cut? So this is showing that we'll stop fast enough. We'll stop by time 2 ln n. But now for success probability. Okay, let me show. But for success probability, a fixed min k cut survives for time t with this probability, and this is n to the minus 2k at this time. So we've rephrased Carter-Stein analysis in the continuous setting. Okay. So now suppose we have the second property that we stated, which is there are only a linear number of small cuts of the graph of this size. So now I want to claim that actually we get a much so I want to claim that each of these small cuts survives by time t with probably e to the minus t. Again, it's a very simple statement. So that's nice because since there are only a linear number of small cuts, you should expect them all to die out by time ln n. Because again, this by ln n, this probability is 1 over n, and only n small cuts. And finally, what about the cuts of size less than the k bar? Well, there's almost k minus 1 of them by a simple argument. If there were more than this many, then these cuts themselves would form a smaller min k cut. So with these three properties, we get that by time t star star, which is 1 ln n, which is much less than the original bound of 2 ln n, all the vertices, remaining vertices, have degree at least 2 minus epsilon n the k bar, because we've contracted all the small cuts in the graph. So that gives us the factor 2 boost that we want in the degree that we were trying to look for. And imagine that by time ln n, there should be roughly root n vertices remaining. So we go from root n to 1 at a much faster rate. Actually, we go down to twice as fast. So going from ln n to 2 ln n actually proceeds twice as fast, and we get stopping time of 1.5 ln n with high probability. So again, repeating the analysis, we get this probability surviving. And to go fully down the n to the minus k, essentially we should be taking advantage of this argument at any point in time, not just at time 1 ln n. So we'll skip today. What we do is we track a differential equation. We prove we have some concentration measure argument to prove that with high probability that we actually the algorithm will follow this differential equation. Okay, so we call this our approach. And we'll briefly go over the second property. So again, this is our statement. And just to sanity check, there are for the cycle, there are no small cuts because then k bar is 1, and all cuts are size at least 2. And for the clique, there are n small cuts because lambda k bar is roughly n minus 1, and every singleton cut is also size n minus 1. Here, any 2 vertices induce a cut of size roughly 2n, which is no longer a small cut by this definition. So you can see that the epsilon is required, and also linear is also required. So this theorem is tight in those 2 settings. So the first idea we have in mind is that if we view the set of small cuts as like small 2 cuts as sets on a universe of vertices, subsets of vertices on the universe of vertices, then these sets cannot intersect in too many complicated ways. In other words, if you view the Venn diagram of any k over 2 of these sets can only intersect to give at most k occupied regions. Why is that? That's because otherwise we will get a k cut of value at least k at most k times lambda k bar by just taking the union of all the cuts. They'll give us k regions, and that's exactly a k cut. And we only have k minus 2, k over 2 of these cuts. So we multiply this by the size of each cut, and we get less than half. The second proof idea we'll need is the idea of sunflowers. So I'll just skip the slide out of time. And essentially, why are sunflowers useful? So essentially, we want to show that the set of small cuts does not contain a large sunflower. So essentially, our proof is essentially this diagram here, and this explanation. So due to time constraints, I'll also skip this talk, but it's in the paper. It's very simple, just like one paragraph. So with these two ideas, we will apply these two observations on the set of small cuts, and it turns out these two observations are suffice in any set system on n elements to get that. Again, so what we show is that any set system satisfying these two properties will have a linear number of sets. In particular, the set of small cuts will also satisfy this. So this is a simple inductive argument that we make in the proof. Yeah. So that's the high level algorithm, high level of our analysis. And so open questions is, so for some open questions, can we improve this bound can we improve this n to the k plus literal 1 bound to get the tightest possible bound of n choose k? Again, that's matched by the cycle. So with David Harris, we've actually shaved off this little 1 factor, so we get a bound of n to the k times a constant depending on k. So in stock 2020, okay. So in stock 2020, in the presentation I've asked, what about a 1 plus epsilon approximation in time FET and FET time? So remarkably, this has been solved in the 2P and Fox 2020. And finally, what about the deterministic algorithm to get the same n to the k bound? So currently the best is n to the 2k. And that concludes my
talk. Thanks very much, Jason, for the very good talk. And now we have 1 or 2 minutes for questions. So Uri Zwick asks, for which values of k is the new algorithm the fastest no algorithm?
So for k at least 3, it's already fastest. Previously, no cubic algorithm was known for the case k equals 3. Which is interesting because when k is 2, a near linear time algorithm is known. So it's instead of n squared, at least for the min-cut, the global min-cut problem. But once we go from k equals 2 to k equals 3, we go from near linear time to n cubed time. So it might be the case that actually the right answer is n to the k minus 1, algorithmically at least, not n to the k. But of course, the extremal bound is n to the k because of the cycle.
Thanks. So if there are no more questions, then I think that this session.
There is one more question.
Oh, one more question. Okay.
Just that is maybe possible. Yeah. I personally think n squared is probably possible for k equals 3. I think my personal hunch is that the right answer should be n to the k minus 1. Because this matches. You might be able to save a factor of n somewhere in a smarter algorithm. You won't be able to use Carver-Sines algorithm, but in a smarter algorithm, you might be able to save a factor of n somewhere. So I think personally the best algorithm bound and with the corresponding lower bound is n to the k minus 1. But I think Mn itself will be pretty interesting.
Great. Okay, so if there are no more questions, then thanks again to the 2 speakers of this session. The session has ended because now there's the business meeting.